Okay, so this is potentially an extremely boring paper, so I thought I'd try and make it a little bit more interesting. And I've got some volunteers. If my volunteers could come up, and we're going to do this. By example rather than anything else. So we're going to start off. This is generating passengers for simulation, and we're going to start off with passengers with a constant inter-arrival time, and basically they should be 5 seconds apart. I think you're over here, Caroline, somewhere. What letter are we? You're F. You're there. That's it. You're there. Okay. Everyone but Caroline was briefed, so she's going to be a little bit last minute. So you can see we've got passengers, and this is when they arrive. This is the timeline, and they're every 5 seconds apart. Yeah, because that's the simplest way of generating passengers. So basically, every 5 seconds, a new person will arrive in the lobby. Okay, so that's one. If you could start going into position 2, please. Okay, position 2. Okay, so now we've got random inter-arrival. We got passengers' arrivals under a rectangular PDF process. So basically, whereas we had 5 seconds apart, now it could be anything between 0 and 10 seconds. Yes, and so they look like that. So again, they're all arriving at the lobby here, pushing the button in different times. So they're slightly different. And of course, this will make a slightly different result when you do your simulations, which is why it's important. That's the way we're here. So if you could go to position 4, please. There's no 3. Okay, so you should be all up in lines now. Okay, so if you apply the standard Poisson formula, basically you get groups of people. You should be in a straight line behind each other. You're actually, that's it, like that. Like that. Okay, and if you might have noticed we've got some extra people on the end here now. Yeah, that's because when we use a Poisson approximation, we don't necessarily get exactly the right number of people, which is actually something that we're trying to solve for this particular paper. So that's the Poisson one, and now we're going to rearrange the formula, do a little bit of maths, and rather than having the number of people as the variable, we're going to have the distance between the people as the variable. So if you could go to the next position, which is what were we? 5. Is it 5? Yeah, 5. Let's see if we go to 5. So this is passenger arrivals assuming a random inter-arrival time with exponential PDF, probability distribution function. Okay, so now it's more to do with, the Poisson bit is more to do with the distance between people than actually the numbers of people in a group. And that's just a mathematical rearrangement of it. And just finally, if you could go to the final one, which is figure 6. This is an example of, where are you trying to go, Gina? Okay, so this is actually how Elevate does it, which is basically takes a person, throws a dice, and decides where on that timeline that person's going to be. So lots of different ways of generating passengers in simulation. And having done the fun bit, I'm going to then get the intelligent bit Lutfi is going to do for us. Thank you very much. My volunteers could have a round of applause. Thank you.
Okay, good morning, ladies and gentlemen. Nice seeing you. Thank you very much, Richard, for a very animated presentation. I'd like first just to thank our co-author, Engineer Ahmad. Is he? Could you stand up, please? Where's Engineer Ahmad? Engineer Ahmad helped us with crunching the numbers and so on. It's only fair that I ask him to stand up. There wasn't enough time to include him in this presentation. He did a lot of the number crunching. So I was very, very pleased to do a paper with Richard. And we were talking this morning, it was all smiles and And the trick is, which he didn't realize, is that that will allow me to criticize the paper and then criticize simulation without him realizing. So, okay, so we saw possible models for generating passengers. Once you go into simulation, you've got to generate passengers. You've got to generate when they've arrived, and eventually you've got to generate how many arrived in the group. That's the new stuff which has been developing. We're going to talk a bit about stretching, shrinking, and how to be flexible in life. Hypothesis testing, there's something called the KS test, the Kolmogorov-Smirnov. Not that Smirnov. John Stopes. So, how many passengers can we, how many methods, how many different methods? Well, when you've calculated the round trip time, and we've all calculated the round trip time, you saw the classical equation yesterday, you're implicitly making the assumption that it's a constant arrival, so people is arriving like the first arrangement that you saw, where they're arriving, we're assuming that, and we're assuming that the round trip time is constant. And it's not, the round trip time is a variable. Because in every journey, people select different destinations. So the length of a round trip is always varying. And what we're really dealing with is the average. We're assuming a uniform density function. We can generate in accordance with uniform, Poisson, exponential inter-arrival times. These are the things which Richard showed you. And a recent development has been the batch arrivals. So in reality, people arrive in groups. When you're going out for lunch and coming back, you're usually with friends and so on. So the model has changed slightly. So that's the constant arrival. That's what we're assuming when we actually calculate the round trip time. You're making that assumption implicitly. The people are well behaved. They don't arrive in batches. Every person arrives on his own or her own. And they actually have a constant inter-arrival time. Very well behaved. Beautiful for calculating the round trip time. But that's not reality. So we can either have a uniform distribution function, and we can have a Poisson. Now, if you look carefully at this point here, you will see that there's more than one passenger arriving at the same time. That's the Poisson model. A modified Poisson, which uses the inter-arrival time. Now we're looking at the time between passengers, and this is actually quite widely used as an arrival model, where we're looking at the time between arrivals. Now, recent work which was done in Finland, and a paper was published by Kuusinen and others from Connie, looked at the size of batches, and in fact people arrive in those batches. And what this means, there's a very high probability in this building that it will be one person arriving, which is what, around 65%? But you do have a probability of 20% people arriving in a batch of 2. And then you have a probability of 10% people arriving in a batch of 3, and so on. Now, that's a better representation of how people behave, especially in offices at lunchtime. And if you start generating passengers in accordance to a batch arrival, that's what you see. You see people arriving 2s. Are there any 3s there? Can't see any 3s. It's unlikely. But we have 2s and 1s. So every circle is actually an arrival. Now, stretching, shrinking, in order to adjust the numbers, we need to stretch and shrink. But I saw a lovely video when I was in Finland recently, and I thought it gave me a very interesting idea in Helsinki. It was an interesting idea how people should be flexible. Very windy day. So it's just an idea how people have to be flexible, how it's a good idea to be flexible. And one of the problems that Richard faced when we started discussing this problem is that he said, I have a problem. When I generate passengers randomly, I'm supposed to have 60 passengers, let's say, in 300 seconds. So one passenger every 5 seconds. Once you go to random, you can't actually guarantee that you'll get 60 passengers in 300 seconds. So we need a trick. We need a trick to adjust the numbers and bring them back to the numbers that we want. And the easiest way is just to do like you stretch a rubber band. You can see as we're stretching, we're just basically taking every point there, and it's corresponding to a point down there. So like you hold a rubber band in your hand and you start stretching it, Or if you wash a shirt or something and it's low quality, it will shrink, and you'll get a smaller. And that's the easiest method. You find the factor that you want to shrink by or stretch by, and then you adjust the numbers. And that's an example there. So if you look at the arrivals, these are the original arrivals. And we're getting more than what we want in 60 seconds, or we're getting more passengers. So if we shrink them, you get the upper line where they've been. And every point corresponds to that point corresponds to that point there. And obviously this point corresponds to this point there. And once you've done that, you restore the original number very simply, very easily. And the same has been done as well with batch arrivals. So you see that the top one has taken around 990 seconds. The lower one has been adjusted, and it gives you the right numbers in the workspace that you want. And finally, I'm going to talk about hypothesis testing. Statisticians, they love the term hypothesis testing because what they're basically saying, if I have a process, a random process, how does it behave? Does it behave in accordance with a certain model? And there is a test. There's a test which actually looks at it and confirms whether it follows a certain probability distribution function. Alexandros and Gina, they did some work in the late 70s, and they used what's called the chi-squared test. Now, the chi-squared test is no use if you have the intensity varying throughout the day. So a much better way was to use the KS test, the Kolmogorov-Smirnov test. And the advantage of this test, it can deal with varying numbers. You'll look here, for example, during this period of time, the arrival rate has increased and reduced, and it's very difficult to apply a chi-squared test. So the KS test is a much better test for that sort of application. So to conclude, there are a number of different methods for generating passengers in software. You can use constant, uniform, Poisson, exponential, and also the method that Richard mentioned in Elevate. Batch arrivals now are much better representation of reality. Talked about shrinking, and I've talked about the KS test to check the hypothesis. That's the end of the first presentation. Thank you much for your attention.